Dear students, welcome to my 5th class on Module 2, Fourier Series. In this lecture video, we're going to discuss about off-range Fourier Series. So first, we will learn what is off-range Fourier Series. When the function f of x is defined in the interval 0, pi or 0, L, then those kind of functions can be expressed as only in terms of sine or cosine series only. So these kind of series are said to be off-range Fourier series. So the first concept is here off-range cosine series. If f of x is defined in 0 less than x less than pi, then the off-range Fourier cosine series is given by f of x is equal to a0 by 2 plus summation n from 1 to infinity an cos nx. To find a0 and an, the formulas are a0 is equal to 2 by pi integral 0 to pi f of x dx, and an is given by 2 by pi integral 0 to pi f of x cos nx dx for n is equal to 1 to 3. In the same way, if the same function is defined in the interval 0 less than x less than L, then the off-range Fourier cosine series is given by the formula f of x is equal to a0 by 2 plus summation n from 1 to infinity an cos n pi by lx, where a0 is given by 2 by L integral 0 to L f of x dx, and an is given by 2 by L integral 0 to L f of x cos n pi by lx dx for n is equal to 1 to 3 and so on. So now off-range sine series. The function is defined in the interval 0 less than x less than pi. Then the off-range sine series is given by f of x is equal to summation n from 1 to infinity bn sine nx. So in this case the bn formula is 2 by pi integral 0 to pi f of x sine nx dx for n is equal to 1 to 3 and so on. Similarly, the same function is defined in the interval 0 less than x less than L. Then the off-range Fourier sine series is given by f of x is equal to summation n from 1 to infinity bn sine n pi by L into x. So in this case, to find the value of bn, the formulas are 2 by L integral 0 to L f of x sine n pi by Lx dx for n is equal to 1, 2, 3 and so on. So now the problems on off-range Fourier series. The first problem is find the off-range cosine series of f of x is equal to x minus 1 whole square in 0 less than x less than 1. So here, so clearly this problem is an arbitrary interval case. The value of L will be equal to 1 here. So given the function is x minus 1 whole square in the interval 0, 1, it implies that the value of L is equal to 1. So now take the formula of off-range Fourier cosine series, that is f of x is equal to a0 by 2 plus summation n from 1 to infinity an cos n pi by lx, and call it as equation number 1. So now our job is to find the Fourier coefficients a0 as well as an. The formula for a0 is 2 by L integral 0 to L f of x dx. Now replace L is equal to 1 and the function f of x is equal to x minus 1 whole square. So we got 2 by 1 into integral 0 to 1 x minus 1 whole square dx. It will be equal to 2 into x minus 1 whole cube by 3 with the limit 0 to 1. So 2 by 3 I'll keep as it is. So applying the upper limit x is equal to 1, we got 1 minus 1 whole cube. Lower limit replacing x is equal to 0, we got 0 minus 1 whole cube. The value of a0 is 2 by 3 here. So now finding an. So an is equal to, we have 2 by L integral 0 to L f of x into cos n pi by Lx dx. So now replace L is equal to 1 and the function f of x is equal to x minus 1 whole square. So we got 2 by 1 integral 0 to 1 x minus 1 whole square into cos n pi by 1 x dx. So to solve this one, I am going to apply the Bernoulli's condition. So taking x minus 1 whole square as u and cos n pi x as v, applying the Bernoulli's condition. So after integration, we'll be getting the equation like 2 into x minus 1 whole square sine n pi x by n pi minus 2 times of x minus 1 into minus of cos n pi x by n pi whole square minus 2 times of 1 minus 0 into minus sine n pi x by n pi whole cube with the limit 0 to 1. So now after applying the limit, this sine n pi will become 0 for both upper and lower limit. So directly I am replacing 0 here only and dealing with only this term, that is 2 times of 2 into x minus 1 cos n pi x by n square pi square with the limit 0 to 1. Applying upper limit, so we got 4 by n square pi square into 1 minus 1 cos n pi minus lower limit replacing x is equal to 0, we got 0 minus 1 into cos 0. So we got 4 by n square pi square into 0 plus 1. Therefore the value of an will be equal to 4 by pi square n square. So therefore f of x will be equal to 1 by 2 into 2 by 3 as a value of a0. plus summation n from 1 to infinity 4 by pi square n square into cos n pi by 1 into x. So after simplifying this, we got x minus 1 whole square is equal to 1 by 3 plus 4 by pi square summation n from 1 to infinity cos n pi x by n square is the required Fourier cosine expansion. Example number 2. Expand f of x is equal to e power minus x as a half-range Fourier sine series in the interval 0, 1. So now, first take the formula of half-range Fourier sine series in the arbitrary interval 0, L, because here they are given that L is equal to 1. So f of x will be equal to summation n from 1 to infinity bn sine n pi by lx is a formula. So now take the equation f of x is equal to e power minus x in the interval 0, 1. It implies the value of L will be equal to 1. So now replace this data in the Bn equation. So consider Bn is equal to 2 by L interval 0 to L f of x sine n pi by lx dx. So replacing L is equal to 1 and the function f of x is equal to e power minus x. So we got 2 by 1 into interval 0 to 1 e power minus x into sine n pi x dx. So now after integration we got 2 into e power minus x by minus 1 square plus n square pi square into minus 1 sin n pi x minus n pi into cos n pi x with the limit 0 to 1. So now applying upper limit, replacing all x terms by 1, we got 2 by 1 plus n square pi square into e power minus 1 sin n pi minus n pi into cos n pi, and lower limit is e power 0 and into minus sin 0 minus n pi cos 0. So sin n pi is 0, sin 0 also 0, cos n pi is minus 1 power n, cos 0 is 1. So we got 2 by n square pi square plus 1 into 1 by e minus n pi cos n pi plus n pi cos 0. So we got 2 n pi by 1 plus n square pi square into minus 1 by e into minus 1 power n plus 1 after simplification. So by taking LCM, we got Bn is equal to 2 n pi by 1 plus n square pi square into e minus of minus 1 power n divided by e is the required value of Bn. So therefore, the f of x will be equal to summation n from 1 to infinity 2 n pi by 1 plus n square pi square into e minus power n divided by e into sin n pi x, or e power minus x is equal to 2 pi by e into summation n from 1 to infinity n e minus power n by 1 plus n square pi square into sin n pi x is the required Fourier sine series for the given function e power minus x. Thank you.